In this video, we're going to calculate the frequency, energy of a photon, and the color of light that an excited potassium ion emits with a wavelength of 427 nanometers. So to begin this, we're going to use our equation, which is nu, or frequency, times lambda, or wavelength, is equal to c, or the speed of light, which in our case we'll use this term 3.00 times 10 to the 8 meters per second. Now, since we've been given a wavelength, you can see right here, this will go right here. So in order to solve for our frequency, we're going to rearrange this to make our life a little bit simpler. So our frequency is going to be equal to the speed of light divided by our wavelength. Now, one important thing to note is going to be our units. So we see that from our speed of light, we have meters and per second. So in the case of our lambda and our nu is going to be already in per second, perfect. But our lambda, we need to make sure that we convert that into meters. So in this case, we're given 427 nanometers. So the first thing we need to do is convert that 427 nanometers into meters. The way that we do that is just with this ratio, which is we know that for every 1 meter, it's going to be 1 times 10 to the 9 nanometers. Now when we multiply this out, we'll see that our nanometers will cancel each other out because we have 1 on the top and 1 on the bottom of our fraction. So this will become 4.27 times 10 to the negative 7 meters. Now we can plug this into our equation, where nu is equal to the speed of light, 3.00 times 10 to the 8 meters per second, divided by our new number, our wavelength, 4.27 times 10 to the negative 7 meters. And this is going to come out to 7.03 times 10 to the 14 per second. So now we've been able to solve for this first part, which is the frequency. Have that done. Now let's move on to the energy of a photon. This is going to require a different formula. So we're going to call this energy photon. This is going to be equal to Planck's constant times frequency. So Planck's constant, we're going to use this number, which is 6.626 times 10 to the minus 34 joules times seconds. And our frequency will still be in the units of per second, like we had just from above. And then energy is going to be in joules. So now let's plug in the information that we have. We have our frequency, which we got from right here, the previous part of the question. We already have the constant, so now we can simply solve for energy. So I'm going to call this E with a little pH down there to show photon. This is going to be 6.626 times 10 to the minus 34, joules per second, times our number from up above, 7.03 times 10 to the 14 per second. Now we want to make sure that our units are okay here. So we know we need to end in joules. So as we look at our two numbers, when we multiply them, we have seconds and we have per seconds, which means they're going to be on top and bottom of our fraction. Because of that, these two will cancel each other out when we multiply them, only leaving us with what we want, which is joules. So everything is going to add up correctly. So once we multiply those together, we're going to get E of our photon is going to be equal to 4.66 times 10 to the minus 19 joules. So now we have solved for the second part, which is going to be the energy of a photon, which is right here. Now on to our last one, which is the color of light that this is going to show. Now from up above, again, we are 427 nanometers. Now the visible spectrum of light, those colors that we can see, goes from about 400 nanometers to about 750 nanometers. On the far left is going to be our purple color or indigo color, and on the far right is going to be our red, close to black color. Because we're at 427, that means we're very close to this purple side. We know that this should emit a color that is very similar to purple. Some might call it indigo. So we will just say that 427 nanometers should be about purple/indigo. And with that, we have now solved for all three of our quantities. We solved for our frequency, we've solved for our energy of a photon, and finally the color of light that a photon will emit at 427 nanometers.